All right, so indefinite integrals, formulas, and properties. So theorem one states that if the derivatives of two functions are equal, then the functions differ by at most a constant. Now we're going to use this symbol, and this is our symbol. It's kind of a fancy, kind of like curly Q thing. That's going to be the indefinite integral, and it's the indefinite integral of f of x dx. Okay, and we're going to use that indefinite integral to represent the family of all antiderivatives of f of x, and we're going to write that. So again, we start here like this, the indefinite integral of f of x dx, and we're going to come out with a capital F of x plus some c. Now, if the derivative of f of x, so if we're taking the derivative of this, is equal to f of x, okay? So that's kind of the key thing. We have to take the derivative. Now, we know that the derivative of a constant goes to 0, so we don't have to worry about that. So that's just some c. And so when we take that derivative, we better get out our f of x. So derivative of the capital F of x should give us the little f of x. Now, this is the integral sign, like it says here. And the function little f of x is called integrand. Now the symbol dx, which is this piece inside of here, indicates that antidifferentiation is performed with respect to the variable x. So we could have done it with respect to y, and then we'd have probably an f of y instead of f of x. And so it all depends on units. So we can have different units and variables and stuff. So that's going to be a nice thing we can do. And the arbitrary constant, our c value that, when you take the derivative goes to 0, is called the constant of integration. Now, if we remember previously, when we said, okay, the integral of x squared dx was x cubed over 3 plus c, well, taking that derivative, we get that. And so that's kind of why that works. That's our constant of integration. Now, like I was mentioning, we can use any variables. It doesn't matter. Instead of x, we can use t, and then we'll take dt. Or we can use u. We can use du. And so it works the same way no matter if we have, t's or u's or x's or even y's. We can do all the same things. Now, the fact that the indefinite integration and differentiation are reverse operations, except for the addition of the constant of integration, can be expressed symbolically as the following. So basically, this derivative is basically doing the reverse of this integration. And so then what happens is when you take the derivative of the integral, we get back whatever's left, and whatever's left is just our f of x. So the derivative of the indefinite integral of f of x is f of x. And so that's what that's saying. If you take the derivative of that integral, that's what we get. And if we take the integral of the derivative of d of x, we get back f of x and plus some constant. Okay, so the indefinite integral of the derivative of f of x is f of x plus some constant c. Now, there's certain functions that we need to learn how to do this with, and some of them we have here are x to the n dx. Now, when I did earlier, I did it, and I remember I had like an x squared over 3, or actually 3x squared, I believe is what it was actually. Where'd my eraser go? What we did was we added one here, and that became x cubed. We divide by whatever that is, and we still have that 3 out in front. Okay, so that's what we're doing here. We're taking and adding one here, so it becomes n plus 1. We divide by n plus 1, and we add some value c. Again, that's our constant of integration. Now here, n cannot equal a -1. That's kind of a key thing. So the n cannot equal -1. All right, what about the integral of 1 over x dx? All right, well, that's going to be ln of absolute value of x plus c, and we'll see in here on the next slide what that all really means and what that represents. And here, of course, x cannot equal 0 because we can't divide by 0, and also we can't take the ln of 0. And over here, the integral of e to the x dx is going to be e to the x plus c. Now, if we take the derivative of e to the x, what do we get? Well, we get e to the x. And so basically it's going to go the same way, but now we have this constant added on to the end after we take the indefinite integral. Okay. Now, what I was mentioning here with this number 3, and I guess I went 1, 3, 2, but it's 1, 2, 3, but whatever. So formula 3 involves the natural logarithm of the absolute value of x. Now, although the natural log function is really only defined for x greater than 0, f of x equals the ln of absolute value of x is defined for all x's except for x equals 0. And again, because we can't divide by that 0. Oops. So we have that vertical asymptote right here. Now, uh, with the f of x, it's decreasing for x less than 0, but it's going to be increasing for x greater than 0. So we're going negative this way, and we're going positive this way. So therefore, the derivative of f, which is found by formula 3, the f prime of x is equal to 1 over x. And so when we take this derivative, we get this function, and we have the upper piece, and we have the lower piece, okay? And it's negative for x less than 0, and it's positive for x greater than 0. So that's kind of why we get what we get here. And so when we take the integral of this and take the integral of this, what we get is this here. We get the ln absolute value of ln of absolute value of x, and then plus a constant, okay? And then if we go that way, we just get 1 over x. All right, some properties. I'd used this earlier on an example, and these are for indefinite integrals, and so we're going to have some constant k. Okay, so if we have k times f of x, then what we can do is we can pull this k out in front, and then we just take the integral of f of x dx. And so that's going to be nice because then we don't have to think about, okay, well, it's 3 times x squared dx. Well, we pull that 3 out in front, and now we're only taking the integral of x squared. That's all we have to worry about. Once we find that, then we can multiply by our 3, our k, whatever value k is. Okay. Now here, this one is nice because now we have the integral of either the sum or the difference of two functions. And what we can do is we can split it into the sum or the difference of the integral of each function by itself. That makes it so it's a lot easier, so we don't have to think about, oh, what is there anything I need to do here? Well, no, I just take the integral of the first function and then either plus or minus the integral of the second function. And written out here in long form, this property here states that the indefinite integral of a constant times a function is the constant times the indefinite integral of the function. Okay, basically, it's what it's showing here. And property 5 says the indefinite integral of the sum of two functions is the sum of the indefinite integrals, and the indefinite integral of the difference of two functions is the difference of indefinite integrals. So it doesn't matter if it's a sum or difference. If you have a sum of two together, then it's going to be the sum of the two separated. If it's a difference of them together, then it's the difference of them separated. All right. Now, it says that we can remove a constant. So we can pull out that 5. Okay, well, that works really nice, but it doesn't say we can pull out a variable. So we cannot pull out an x. That doesn't work. We have to keep that x within that thing. So only works with constant, doesn't work with variables. So that's a key thing to remember when you're doing this. A lot of people think, oh, it'll be easy to do that and make it easier. Well, yeah, it'll make it easier, but it doesn't work. You can only do it with the constants such as 5. You can pull that 5 out in front and that works. Okay. Now, the indefinite integral of a constant function with a value k is going to be k times x plus c. So basically, if we're taking the integral of just a constant, 1 dx, well, that's really just the integral of dx. Well, that's just going to, when we do that, if we think about that, that's x to the 0 because x to the 0 is 1. If we add one more to that, that's going to be x to the first, and we divide by 1, so that's x. And now if we had some k out in front of that, k times something, that's just going to be kx. So then we'd have our k here. And then we also have to have our constant at the end there, our constant of integration, okay? Now, similarly, using property 5 and the formulas 2 and 3, if we have, some e of x plus 1 over x, and we're adding the two together and we're taking the integral of that, we just split it into the integral of the first plus the integral of the second. Well, the integral of the first is just e to the x plus c1. Integral of the second is just ln of absolute value of x plus c2. Now, this constant plus this constant is still, guess what, a constant. And so we're just going to rewrite that as just a c. We're just going to leave it as 1c. And so now we just have e of x here plus ln of absolute value of x plus c is what this is going to be equal to. So we can split apart a sum, and then when you do that, you're going to get two constants, or if you have a whole list of them, you're going to get a bunch of constants, but in the end, it's just going to be a c. We're just going to replace all of those with a c, and then we don't have to worry about anything after that. And it's just, that's going to be our final thing. Okay. All right, so let's do some problems here. So we're going to find the indefinite integral of 2 dx. All right, well, what is 2? Well, that's a constant. So remember, we can pull that out front. And so that's going to be 2 integral of dx. Now the integral of dx is going to be just x, and it's going to be x to the first over 1, but it's just x. And so that's going to give us 2x, and then we have to remember and add in our constant of integration. Okay. What about b? Make sure I go to b, not d. All right, so here I've got a constant, so I can pull that out front. And so what I'm going to do is really just kind of rewrite it down here and then write what I'm actually taking the integral of as far as I'm simplifying it at this point in point in time. So now I have 16. Well, the integral of e to the t is e to the t, and then I just have plus c. Okay, and that's all I have to have. That would be my answer. And again, we're just using the properties they gave us. You know, x to the n, we do this. E to the x, we have this. 1 over x, we have this. And then if we have a constant, we do this. And if we have a sum or difference, we do this. And so that's all we're doing at this point in time. So let's do c. So now we have a 3 we can pull out, and that's going to give us x to the 4th dx. Well, that's going to be a 3. Now, x to the 4th is going to be what? That's going to go x to the 5th, and then it's going to be divided by a 5 plus c. And so we can write this as 3/5 times x to the 5th, or 3x to the 5th over 5. It doesn't matter. As long as we realize that the 5 is in the denominator, the 3 is in the numerator, it doesn't matter how we write that, and that would be our solution there. Okay. All right, D. D looks like it's going to take a little more space. So let's go up here and do D up here. So now that's a difference, and then that's a sum. We've got some constants here. So let's pull that out. So we'll have a 2 integral of x to the 5th dx minus 3 integral of x squared dx plus, and then we have 1 times the integral of dx. Okay, so the first one here, well, that's going to be 2x to the 6th over 6 plus c1 minus 3. Now this is going to give us x to the 3rd over 3, and then plus c2. And this is going to be plus 1 times, now it's going to be x, and then it's going to be over 1, but over 1 doesn't mean anything, and then plus a c3. All right, so what am I going to do? Well, I'm going to reduce. Let's go ahead and use a different color and cancel stuff. 2 will go in here once, 2 will go in here 3. Those 3's both cancel to 1 and 1. And I'm going to take this 3, this 2, and this 1 C's, and I'm going to rewrite that as just 1C. Okay, so now I'm going to rewrite this as what? X to the 6th over 3, and then I have a minus x cubed, and then I have plus x plus c. So I've taken this, this, and this, and combined it into just a c. Okay. All right, so that's D. Now E, let's see here. Let's try it here and see if we have enough room. So now I can pull out a 5. That's going to be 1 over x dx. I can pull out a 4. That's e to the x dx. Okay. Well, 1 over x, what's that? That's ln of the absolute value of x. So that's going to be 5 ln absolute value of x, and then plus a c1. And we have minus 4. Now this e to the x is e to the x, and I'll call that plus c2. Now c1 plus c2, again, I'm just going to say, okay, well, let's call that c. So now that gives me 5 ln absolute value of x minus 4 e to the x plus c, and that would be my answer. Okay. So that's how we do these 5 different integrations and evaluating the indefinite integral. Okay, so let's stop there and we'll come back for some more.